So till the last class we finished about the classification of solids, space lattice, types of unit cells, right? And we have done some numerical problems on the packing efficiency also, and the types of unit cells, density formula also we have done the numericals. So today we'll continue with the other topic, then we'll do some more numericals, okay? So today we'll start with the topic close packing in the solids. So what is the meaning of close packing in the solids? The arrangement of atoms in the given solid, that is only the close packing, right? So we can arrange the given atoms in the given solids in the different directions. So that is what we are going to study in the close packing in the solids. So again, the close packing in the solids we study in the three different types: one dimensional, two dimensional, three dimensional. So again, the two dimensional we have the two different close packings. One is a square close packing, the other one is a hexagonal close packing. Again, in the three dimensional we have the two different patterns, ABC ABC and the AB AB. So there's a complete chart about the close packing in the solids in the 1D, 2D and the 3D. Okay, and each and every packing we have the different coordination number and different packing efficiencies. So first let us start with the one dimensional itself. So one dimensional means what? Arranging the atoms in a single row or in a single column. There is a simple one dimensional close packing. Okay, suppose if we take some atoms, if you arrange them in a particular row, so that each atom can touch directly with how many atoms? If you take one particular atom in the one dimensional close packing, each atom can touch directly with how many other atoms? Two other atoms. Good. Then what is this directly touching one? It is called as a coordination number. So coordination number is nothing but the number of atoms or nearest number of atoms is called as a coordination number, right? The nearest number of atoms around the given atom is called as a coordination number. So in the case of one dimensional, the coordination number is 2. Okay. The next one, two dimensional. So in the case of two dimensional, we have the two different types of packing, right? One is a square close packing, the other one is a hexagonal close packing. So what is this square close packing? What is this square close packing? Just we'll take one row. That A row is the same. Again below also we'll place the second row exactly in matching of the alignment of the first row. Okay, so I'll draw the diagram in the notepad itself. So if you see the square close packing, how it looks, first we'll take one row here. Can you see the writing part? Can you see what I'm drawing on the screen?
Yes, sir.
Okay. So first we take one dimensional one row. The second one also will take exactly below the first one. The second atoms also will place exactly below the first one. So this type of arrangement is called as an A type arrangement. This is exactly below the first one we are placing the second atoms also. So this is a A, this is also A, and this is also A. So this type of packing is called as a square close packing. Okay, there will be perfect alignment, right? In this direction there is a perfect alignment. In this direction so there is a perfect alignment is there. Okay, this is only called as a square close packing. Then if you take one particular atom here, if you take this particular atom is contacted with how many other atoms? 1, 2, 3, 4, right? This particular atom is in direct contact with the 4 other atoms. Then what will be the coordination number? Coordination number will be the 4. This is what I explained here. Any doubts in this?
No, sir.
Okay. Then what about this hexagonal close packing? What is the difference between the square close packing and the hexagonal? We'll see here. This is the first row of atoms. Okay, but second row will place not exactly between the first row. We'll place in the depression of the first row. So this is the first row depression. So this is the second row depression. Depression means what? That gap is forming in the first row, right? That is a collision depressions. So this one. So wherever the gap is forming here, we'll place the second row atom in the depressions. So this is a depression. So we'll place here. This is one more depression we'll place here. Like this. That means this is the A type of arrangement. This is the B type of arrangement. Now, where we'll place the second one? Third row here. Where we'll place the third one? In the depression of second, right? So this is a depression of second. So this is also depression of second. Depression of second. So we'll place the third row like this. That means if you see the first one and the third one, both are same only, right? The first row of arrangement and the third row of arrangement both are same. So again, we'll call it as an A. So what is this type of pattern? ABA type of pattern. What is the pattern? ABA type of pattern. So two-dimensional is nothing but in the hexagonal close packing. First we'll place one row, then the second row of atoms will place it in the depression of the first row of the atoms, so that it will have the different arrangement. Again, the third row is placed in the depression of second row, so that the first row and the third row will be aligned in the same way. So this type of pattern is called as an AB type of pattern or hexagonal close packing. Clear?
Yes, sir.
Then suppose you have taken one atom here, like this atom we have taken here. Now tell me how many atoms are attached directly to this? How many atoms are in direct contact with this? One, two, 3, 4, 5, 6. So these 6 atoms are directly in contact with this only, right? The center atom. That means the coordination number is how much? 6. Clear? The coordination number will be 6 in the case of hexagonal close packing. Fine. Or any doubts?
Clear, sir.
Remaining? The area Ramcharan.
Yes, sir.
Any doubts?
No, sir.
Can I clear the drawing part? Because already it is given in the notebook, right? Okay. So next we'll go for the next arrangement. Just wait a minute. Okay. So this is all about the one-dimensional, two-dimensional. Okay. So next we'll go for the three-dimensional. Actually, seeing the three-dimensional in this format is very difficult. So I will show you the video that's better. Okay. So about the three-dimensional close packing, about the FCC and about the HCP. Okay. So before showing the video, first I'll cover the topic voids. Tell me what is the meaning of void? What is the meaning of void? Are the interstices, are the gaps, are the spaces? Anybody, what is the meaning of void? Or what is the meaning of gap? Are the spaces or the interstices? So whatever the empty space is there between the solids in the between the atoms in the given solid is called as in void, right? Suppose you have taken some particular atoms like this. So when you take the particular solid like this, whatever the empty space is forming between the two atoms in the given solid, that is called as in void, right? So what is the empty space here? This is the empty space, or this is the empty space, or this is the empty space, like this. So whatever the empty space is there between the solids, that is called as in void, or the interstices, or interstitial, or the gaps, or the spaces. So voids are two types again. One is the octahedral void. The other one is the tetrahedral void. Okay. So what is the meaning of this n and 2n numbers? Anyone? What is the meaning of n and the 2n? What is the meaning of n and 2n?
Sir, a number of voids.
Number of voids. Good. So if you take,
Voids.
sorry, 1 minute. Okay. So if you take the n value is the number of voids forming in the given solid, where n is the number of atoms in the given sphere. Okay. Suppose n is the number of atoms in given sphere or the given solids. If n number of atoms are there, then how many octahedral voids will be formed? Same n number of octahedral voids will be formed. But if n number of atoms are there in the given solid, how many tetrahedral voids will be formed? Double the number of tetrahedral voids will be formed. Okay, that is a 2n. Now we'll discuss first where will the tetrahedral voids will be formed and where will be the octahedral voids are formed. So if you take tetrahedral void, tetrahedral void means what? Whatever the empty space is forming between the four solids. So this is a tetrahedral void. Just wait a minute. I think it is not clear. Is it clear? The green color? We'll use this color. So whatever this space is there, this is the tetrahedral void. The void space created between the four atoms in the given solid is called as a tetrahedral void. That means 3 atoms will be there in the one layer and 1 atom will be there in the above layer. So whatever the void space or whatever the empty space created between the 4 atoms in the given solid is called the tetrahedral void. So each tetrahedral void is surrounded by the 4 atoms. The 3 atom will be in the same layer, 1 atom will be in the above layer. Clear? Next, octahedral void. In the case of octahedral void, how many atoms will be surrounded? How many atoms will be surrounded? In the case of octahedral void, how many atoms will be surrounded? This is a one layer. This is a one layer. Next above layer will be like this. Just wait a minute. If you take the octahedral void, total 6 atoms will be surrounded. 3 will be in the one layer and the 3 will be in the above layer. So each octahedral void is surrounded by the 6 atoms and each tetrahedral void will be surrounded by the 4 atoms. Okay. So we'll see in the video how this tetrahedral void formation has happened and how this octahedral void formation has happened. Any doubts in the octahedral and tetrahedral? Any doubts?
No, sir.
Shall we go to the video? Can you hear the sound?
The three-dimensional modes of packing can be easily understood by dividing the whole process into 3 steps. Close packing of spheres
Can you hear the sound?
Yes, sir.
Okay.
in one dimension. In one-dimension close packing, there is just one way of arranging the spheres. Here, the spheres are arranged in a row touching one another. As a result, each sphere is in contact with 2 neighboring spheres. Thus, in one-dimensional close packing, the coordination number is 2. Close packing of spheres in 2 dimension. Close packing structures in 2 dimension can be generated by stacking rows of one-dimensionally closed packed spheres, one above the other. This can be done in 2 ways: square close packing and hexagonal close packing. Square close packing. In this type of packing, the second row of spheres is placed in contact with first row in such a way that the spheres of the second row are placed exactly above the spheres of first row. In such an arrangement,
Is it clear now? In the square close packing in the 2-dimensional way, the second row is placed exactly above the first row. Okay.
the spheres are aligned horizontally and vertically such that each sphere is in contact with 4 other spheres. So, the coordination number is 4. If we call the first row as A-type row, the second row being exactly same as the first row, so it is also called as A-type. If we keep on placing such similar rows one above the other, then such an arrangement is known as AAA type of arrangement or square packing. Hexagonal close packing. In this type of packing of spheres, the second row of spheres is placed in a staggered manner such that the spheres fit in the depressions of the first row. If we call the first row as A-type, then as the second row is different from the first row, it can be called as B type. Now, if we place a third row above the second row in the similar manner, we will observe that the third row spheres are aligned with those of first layer, and each sphere is in contact with 6 other spheres. So, the coordination number is 6. Similarly, on placing the fourth layer, we will observe that the fourth row of spheres are aligned with those of second layer. Hence, this type of arrangement is known as ABAB type of arrangement or hexagonal close packing.
Any doubts up to this?
No, sir.
Clear? The type of arrangement of atoms in the two-dimensional. Still anybody has doubts? Dhairya, Ramcharan, Shruti, Vishwanath.
No, sir.
No, sir.
If we compare square close packing with hexagonal close packing, we will observe that empty spaces are less in hexagonal close packing than compared to square close packing. Now, what are these empty spaces and what role do they play in packing efficiency? The empty spaces in between the spheres are known as voids. These voids are responsible for decrease in packing efficiency of the solid crystal. More the number of voids, less is the packing efficiency of the crystal. Now, you must be wondering what is meant by packing efficiency. We have discussed about this in later part of the section. Now let us study about close packing in 3 dimension. 3-dimensional close packing from 2-dimensional square close packed layers. This type of packing is obtained by placing 2-dimensional square closed packed layer above the first one, such that
See, whatever these two is very important now. Previously and all you have seen, right? Close packing. We can understand with the notebook itself, but this arrangement is very important because it's a 3-dimensional one. So in this explains about the clearly about the which void is forming. So when you place the second complete 2-dimensional sheet over the first one, which holes we are covering or which void spaces we are covering, that is very important in this video now onwards. Okay.
the spheres of the second layer are exactly above the spheres of the first layer. In this arrangement, the spheres of both the layers are perfectly aligned horizontally and vertically. On arranging layers one after the other in this pattern, we will observe that each sphere is in contact with 6 other spheres. 4 from the same layer, 1 from the layer above, and 1 from the layer below that sphere. So, the coordination number is 6. If we call the first layer as A type, and since all the layers are also of the same type, this kind of arrangement is known as AAA type of arrangement. On observing carefully, we will find that this arrangement has generated a simple cubic lattice and its unit cell is primitive cubic unit cell. Dimensional close packing from 2-dimensional hexagonal closed pack layers. The 3-dimensional hexagonal closed pack structure can be obtained by placing 2-dimensional hexagonal structures one layer above the other. Placing second layer over the first layer. Let us take a two-dimensional hexagonal closed packed layer A. Notice this layer has triangular voids.
So what is the meaning of triangular voids? I said only about the tetrahedral voids and the octahedral voids, right? Then what is the meaning of triangular voids? Anyone? Whatever the void is forming between the three atoms in the given solid in two-dimensional solid is called as a triangular voids. So if you take this as a two-dimensional arrangement, whatever the void is forming between the three atoms, 1, 2, 3. So this complete blue colors are called as triangular voids. Okay. So octahedral void and tetrahedral void possible in the three-dimensional. Triangular void is possible in the two-dimensional way.
Place a similar closed packed layer in such a way that the spheres of the second layer are placed in depressions of the first layer. As the spheres of the second layer are aligned differently as compared to the first layer, so let us call this layer as B type. On observing, we will notice that not all the triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to a different arrangement and different voids. Voids. There are two types of voids. Tetrahedron voids, denoted by T, octahedron voids, denoted by O. Let us study how these voids are formed. When we place a closed packed layer above the depressions of the first layer, we will notice that at some places the triangular voids of the first layer are being covered by the spheres of second layer. At such places, a type of void is formed. This type of void is known as tetrahedral void, T, since a tetrahedron is formed by joining the centers of the four surrounding spheres. While at other places, we will notice that the triangular voids of the first layer coincides with the triangular voids of the second layer, such that their triangular shapes do not overlap. At such places, another type of void is formed. This type of void is known as octahedral void, O, since an octahedron is formed by joining the centers of the six surrounding spheres.
Is it clear now what is the tetrahedral void and what is the octahedral void? Any doubts in that? Or can I replay the video once again for the voids? Respond. Hello.
Yes, sir.
Can I play the video once again or is it clear? Okay, fine.
Okay, sir.
Okay. So what is the tetrahedral void? What is the meaning of tetrahedral void? So whenever the void space of the two-dimensional sheet is covered with the one atom of the above layer, it will form the tetrahedral void. But octahedral void means what? The third layer placed above the second layer in the three-dimensional arrangement will not cover any of the void space. Right? This is called as an octahedral void. So in the case of octahedral void, total 6 atoms will be surrounded, 3 atoms in the above layer and the 3 atoms in the below layer. So completely the void space, you can see it clearly here. Okay, that is a octahedral void.
Now, in case we need to calculate the number of tetrahedral and octahedral voids in a crystal structure,
What is the formula? If you want to calculate the number of tetrahedral voids and the number of octahedral voids, when we have the n number of atoms in the solid, what is the formula? Anyone? Guys, answer. What is the formula for the tetrahedral voids and the octahedral voids? So if there are n number of spheres in the given solid, tetrahedral voids will be 2n, octahedral voids will be n.
then just knowing the number of spheres will serve the purpose. Suppose there are n spheres in the crystal structure, then the number of octahedral voids generated is equal to n. The number of tetrahedral voids generated is equal to 2n. Placing third layer over second layer. Now let us place third layer over second layer. Stacking of third layer over second layer can be done in two ways. First, by covering tetrahedral voids. Second, by covering octahedral voids. By covering tetrahedral voids. The tetrahedral voids of the second layer can be covered by placing the sphere covering tetrahedral voids.
So this will form the important topic now. That is what I said in the diagram, right? Three-dimensional way. So one will form the FCC structure, the other one will form the HCP structure. So which is forming the HCP structure will cover the tetrahedral voids, and which is forming the CCP or the FCC structure will cover the octahedral voids. So see this video properly from here onwards.
By covering tetrahedral voids. The tetrahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer will get exactly aligned with the spheres of the first layer.
So what is this type of arrangement? AB type of arrangement. What is the name of this arrangement? Is it tetrahedral? Sorry, is it HCP or the CCP? It will form HCP structure.
So, if we can call the first layer as A type and the second layer as B type, then the third layer will also be A type. As the pattern of spheres is repeated alternately in other layers, so this pattern is known as AB-AB pattern, and the structure formed is known as hexagonal close packed HCP structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So the coordination number is 12.
Can you see the structure here? Can you compare this and this here? This one. So how you got the structure? HCP. Any doubts in this? Dhairya, Ramcharan, Shruti, Vishwanath. Unmute yourself and you can give the reply, or else you can keep a message.
Sir,
Yeah. Shruti, any doubts?
no, sir.
Covering octahedral voids. The octahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer are not aligned with the spheres of either first layer or second layer. So, if we call the first layer as A type and the second layer as B type, then this third layer will be C type. Now, if we place the fourth layer over the octahedral voids of the third layer, then the sphere gets aligned with the spheres of the first layer. Thus, this pattern is known as ABC type, and the structure formed is known as cubic close packed CCP or face centered cubic FCC structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So, the coordination number is 12.
So any doubts in the topic? Close packing.
No, sir.
Clear now? I have shown the video because if I explain with the note pattern, it will not be clear. Three-dimensional, right? So we cannot draw the atoms perfectly in the screen. So only I have shown the video. But any doubts now, if you can tell me in that. Any doubts?
No, sir.
Okay. Now tell me. So just we will revise what I have studied in the video. So if tetrahedral voids are covering, What is the type of arrangement? If the tetrahedral voids are covering in the given solids, then what is the name of the type of arrangement of the sphere? And what is the pattern? Is it the HCP or CCP? What is the answer? If the tetrahedral voids are covering in the given sphere in the three-dimensional way, it is called an HCP structure. Okay. And the type of arrangement is what? AB type of arrangement. Okay. If octahedral voids is covering in given sphere, it is called as a CCP type of arrangement. And what is the type of structure? ABC type of structure. Hello, can you hear me now properly? Hello.
Yes, sir.
Yeah, there is some network issue is there. Did you understand what I said before?
Sir, it's a CCP.
CCP. So CCP now what? Covering the octahedral voids. HCP now it is covering the tetrahedral voids. Okay. So that is what I explained here. But these ratios are very important. The relationship between the small r and the capital R. Small r is the radius of the voids and the capital R is the radius of the atoms. So if you take these small r and the capital R in the tetrahedral voids and the octahedral voids, it will be different value. So I have given finally only this one, these two. It's very, very important formula. You'll get the numericals on these two. So small r is the radius of the voids and the capital R is the radius of the atom. In the case of tetrahedral voids, what is the relationship? Small r by capital R equal to 0.225. In the case of octahedral voids, it is equal to 0.414. Okay, so based upon this, you have the limiting ratio. So what is the meaning of limiting ratio or the radius ratio? The radius of cation to the radius of anion. Okay, radius ratio is nothing but the radius of cation to the radius of anion. So R plus by R minus, that is the radius ratio. So in the exam, they will give you this radius ratios, or they will give the radius of the cation and the radius of the anion. They will ask you to find out what is the close packing of that structure and what is the coordination number of that structure. Okay, suppose you have taken the example like this. In a compound AB, the radius of A plus and the B minus are 88 picometers and the 200 picometers. Okay, then what is the coordination number of A plus? How you will find this one? How you will find this? Just you will take the radius ratio. A plus is 88 by A minus is 200. So when you take the radius ratio, you will get 0.44. Now check this tabular column. Where is that 0.44 lies? So where is that 0.44 will lies? 0.41 to 0.73. In between this, you'll get the 0.44. So 0.44 now, what is the type of close packing? If it is 0.44, what is the type of close packing? It is the octahedral. Okay, and the coordination number will be the 6. So like this, you have to find out. So for that radius ratio, what are the 4 different values? 0.155 to 0.225, that is a planar triangular, and the coordination number will be 3. 0.225 to 0.414, that is a tetrahedral, and the coordination number will be 6. 0.414 to 0.732, that is the octahedral, coordination number will be 6. And 0.732 to 1, that is the BCC, that is the coordination number will be 8. This tabular column is very, very important. Okay. So this is only the radius ratio for the tetrahedral. R plus by R minus equal to 0.225. And this is the radius ratio for the octahedral void. R plus R minus equal to 0.414. Okay, these are the values. Any doubts in this?
No, sir.
So what are the topics we covered in today's class? What are the topics we covered in today's class? R plus by R minus, that is radius ratios. First, we started with the close packing in the solids, 1-dimensional, 2-dimensional, 3-dimensional we have covered. And about the different types of arrangement in that, again in the 2-dimensional, we have the 2 different types, sphere close packing and the hexagonal close packing. Right? So in the case of sphere close packing, we have the AA type of arrangement. In the case of hexagonal close packing, we have the AB type of arrangement. So again, when it comes to 3-dimensional, again we have the 2 different types of close packings. In one, we can cover the tetrahedral voids. In the second one, we can cover only the octahedral voids. So whichever is covering the tetrahedral voids of the second layer with the help of the third layer, that is a hexagonal close packing, which will have the pattern like AB. And the next one is covering the octahedral voids with the help of third layer, that is a cubic close packing. Again, they have the pattern of ABC type of arrangement. And afterwards, we studied about the radius ratio. So this is what we covered in the today's class. It's very, very important to study this numerical problem. What are the tabular column I have given for you along with the formulas. In the next class, we'll do some numericals on this. Okay. Fine. Just you ask me now what are the doubts you have. Any doubts? If you have any doubts, you can ask me, or else we'll end the class here. Shruti and Vishwanath. we end the session. Okay. So bye bye.